Hello everyone, my name is Marvin and today I'm going to explain Newton's law of motion. Newton's law of motion is very important in physics, particularly in introductory physics, because they describe the motion of the world around us, the particles that are in this universe, and it has to do with Newton's laws at a very basic level. So let's think about the following problem. So I have an object here, then I drop it. What happens? What happens is the motion of the object is falling down. So it started from the top and it fell towards the earth. Now this thing started at rest, or did it start in motion? The answer is it started at rest because there's no force acting upon it. And this is Newton's first law. First one is object at rest tend to stay at rest, and object in motion tend to stay in motion. So let's see the first one. An object at rest tend to stay at rest. So here's an object. So here an object, and this object is staying at rest. So this is the object, and for example, I throw the object, so it's in motion and it's tending to stay in motion. And in fact, that object, when we are holding it was at rest, and then it started to move, it started to accelerate, but acceleration is in Newton's second law, which we're going to go over later. But if we think about Olympic curling, what exactly it looks like? Well, here's the ice, this is the ice, and you have the stone. And this stone is moving at velocity v. And I think about this object at a later time when it's over here. How fast does it move? So the answer is it will move at the same speed. Why? Because the floor at the stone is moving on is ice, and ice is almost frictionless, and that's Newton's first law. Object in motion tend to stay in motion. So this is ice is frictionless. Ice is frictionless. So yeah, Newton's first law, object in motion tend to stay in motion. And so really what we should put is that here there are no external forces. No external forces. There are no external forces, and there's nothing that's trying to slow it down. There's nothing that's trying to speed it up. But obviously, the example of the object that I showed you earlier, that I dropped it in the first time, we do have an external force which is gravity that's trying to pull it down. So Newton's first law is really no external force. Object in motion tend to stay in motion. Right. So that's Newton's first law, and one way to think about Newton's first law is net force. Net force. Net force. So the net force is equal to 0, and therefore there's no change in velocity, no acceleration too. So no velocity, no change in velocity, and no acceleration. And so let's say you're doing the following experiment. Car at a constant speed. Let's say you're driving down the road in your car at a constant speed in a straight line. So, is there any acceleration for that vehicle? The answer is no, because it's constant and it's driving in a straight line, so there's no force or something. So no acceleration because it's straight line, driving a straight line. So yeah. Next, I still got an example. It's still about the curling sports. So here we have a block. So here we have a block that's sliding along the ice, and let's say that our ice is really frictionless. So the ice is frictionless. Block is sliding along if the block is sliding along at velocity v, so with velocity v, and there's no change in the v, then what we're saying is there must be no net force on this thing. But does that mean there's no force acting on it? Are there forces acting on that stone? Yes. So now we're going to draw the free body diagram. So there is normal force. Normal force going upwards, because the object is in contact with the ice, so there's normal force. And the other is, let me move this aside. And the other is gravity. And this doesn't have to be in contact with the earth because it's pulling downwards, so that's the force you get. And when you draw the free body diagram, make sure you identify all forces acting on the object, because it's going to help you visualize how to handle these force problems. So yeah, you must identify all the forces. So now I'm going to talk Newton's second law. Talk about Newton's second law. Now this is where the fundamental mathematics that we need to understand the universe around us really tied to physics, to understanding not only the motion of an apple falling from a tree, but the moon and orbit around the earth and orbit around the sun, and so forth. And this is the following simple statement. Second law of motion. The simple statement is force is equal to mass times acceleration. So force is equal to so yeah, force is equal to mass times acceleration. We've talked about force before that causes motion, but to be correct, force causes acceleration. Force causes acceleration. And we want to be a little careful about this statement, because what we said just now was if I'm driving down the road at a constant velocity, then the net force on me is zero. Yet, now that there are forces acting on us, what do we mean by that word net? What we really mean is the summation of all forces. Summation of all forces. And we have to take it into account take it into account the fact that those forces are vectors. So this is the net force, or the vector sum of all forces, and if that turns out to be zero, then certainly the acceleration is going to be zero. So in our example of the car driving down the road, let's see if we can think about those forces are, and how might we draw the free body diagram. So let me draw the car. So this is so yeah, let's draw the free body diagram. So the car, the first one is gravity, and there's also normal force. Let me move this aside. And there's friction, which is small f. And the last one is some sort of force that is driving us forward. Which causes by the gas pedal, which moves us forward in motion. So that's it for Newton's second law. So now I'm gonna explain the third law. Newton's third law. So Newton's third law states that action force, every action force, there will be an equal and opposite reaction force, and the other way to say this is there's no isolated force exists. What it means is we have a force, there has to be some other force accompanying it. So Newton's third law states that every action force, there will be an equal and opposite reaction force. And the other way to say this, no. Yes. So Newton's first law states that every action there will be an equal and opposite reaction force. So no isolated force exists. So I'm gonna give you an example. Let's say we have two masses. Let me use this. Two masses. M1 and M2. And they're just floating. Is there any force between these two? The answer is yes. Just pretend it's a planet and they're attached together by gravity. There's a force F12, which is the force on 1 due to 2. And then M2 is trying to pull on M1, but Newton third says that you can't just have that on isolated force. There has to be another force, which is F21, which is the force on 2 due to 1. So if M1 is getting pulled to the right with a force F12, M2 is getting pulled to the left with a force F21. And Newton's third equation is F12 is equal to F21. So now a force of 200 newtons is applied across a box, a 20 kilo box. The frictional force acting on a box is 200 newton. So let's draw it first. 20 kilo box. So a force of 200 newtons applied on it. So here F capital 200 newtons. Then here is the frictional force, which is F equals to 200 newtons. So what is the net horizontal force on a box? So net horizontal on a box is basically the difference between both these forces. So A is 100 newtons. So now B, calculate the acceleration. So use the sum F equals to ma equation. Then just gonna fill in these equations. So 100 equals to 20 A. So A equals to 100 divided by 20, which is 5 meter per second squared. Now see, how far will the box travel after 12 seconds if it continues to accelerate at this rate starting from the rest? So I'm gonna delete this, so the given is V initial is 0, and then the time is 12 seconds, so time is 12. So this wants to find a D. And then the equation we want to use, which is the kinematic one. So the equation is T equals to V initial T plus 1/2 8t squared. So now we're just going to fill in this equation, which D equals to, this is obviously 0, T plus 1/2, the acceleration is 5, T is 12, so 12 squared. So I'm gonna count this. D equals to 1/2 12 squared is 12 squared 144, so it's like this. 144. So then 144 times 5, 720, 1/2 times 720. So it's going to be 360 meters. So the answer is 360 meters. So now I'm going to explain this. A 120 kilogram skater pushes against an 80 kilogram skater. After contact, the 80 kilogram skater was given an acceleration of 1.5 meter per second squared. So A, what is the acceleration of the 120 kilogram skater? So how to find this is you need to use the equation as F1 equals to F2. Then M1 A1 equals to M2 sorry M2 A2. So you're just going to insert the numbers to the equation. So here's 120 A1, which is not given in the question, so we have to find this. So A equals to 80, which is the second mass, A2, which is the 1.5. So now I'm just going to solve this, which is 120 A equals to, sorry, this is negative, solve is negative. Now 80 times 1.5, you see, T times 1.5, 120. So this is 1 minus 120. It's divided, both of them divided by 120, which give us A1 is minus 1 meter per second squared. So we got the acceleration of the 120 kilogram skater. So next B, what force was exerted on each skater? So here we're just going to use sum F equals to MA. So what is the force? We don't know because we're finding this. So equals to, the first one is 120 kilogram, and the first acceleration is minus 1. So the answer is minus 120. The other skater is the same. So F ET times 1.5. So it gives us 122. So it's positive here. So the difference is they have the same force, but it goes to different directions because this is negative and this is positive. So that's it.